Hey folks! Well, we're about to get into a section on compilers and compiling and how the linking and loading and all that sort of thing works. So I just wanted to spend a few minutes going over just recapping the basics of software and hardware and how it all fits together. This should all be total review for most of you, but just so that we're all on the same page going forward. So, again, we've all got the idea that computers are basically just circuits designed to recognize bit patterns, patterns of zeros and ones that represent instructions to carry out little tiny actions. You put millions of these together and you get the behavior that you want. So that I think we can all pretty much accept. Usually when we're thinking about whatever device it happens to be, whether it's a laptop or a phone or a whatever it might be, we typically think of it in terms of a processor, so the brains of the operation, the memory that's holding the data that we're actually using as it's running, a bunch of other devices connected to it, whether it's the screen or mice or keyboards or whatever, everything that can capture data, display data, or store data pretty much. And then communication channels to connect them all together. So we'll refer to those as communication buses, but again, the idea is it's just some conduit, some channel for moving information back and forth between the other pieces. So this is usually talked about as the von Neumann model, and it's the basic model that drives almost all the modern computer architectures. I mean, there are much fancier variants where we look at multiple processors and caches and multiple buses and all sorts of things, but they're basically expansions on this one basic concept. So again, hopefully that part is review, and feel free to read up on it a little bit more if any of it's a little bit rusty, but those are the kind of the basic pieces that we're thinking of. So in terms of what's happening with the software and the commands that we're writing, if we're interacting through touching things, tapping the screen, clicking on something, typing in instructions, essentially we're issuing commands that we want the computer to act upon. So something has to interpret those commands, figure out what it is we want, and make sure that the appropriate actions are carried out. Whether that's running other programs or setting whatever configurations, whatever it might be, something's got to figure out what we're asking for and carry it out. So usually we talk about this idea of the command shell, the program that's reading what we're doing, that's capturing what we're doing, and turning it into instructions for the operating system. The operating system being the collection of software programs that control what the system actually does. So you've got this kind of outer layer where we're doing stuff. You've got the shell that's interpreting what we're doing. You've got this inner layer that's the operating system. And then deep within inside the operating system, you've got the kernel, just a very small basic program that really controls and guides what everything else is doing. So that's the true boss, if you like, of everything that's happening at any given instant. And then you've got a collection of other applications, all of the extra software that we've got installed that can be fired up to do specific tasks for us, the games, the calendars, the browsers, the email, whatever it might be. So again, if we've got this kind of layered view of how the software is working with the hardware, that'll help us when we get to talking about compilers and other fun and wonderful devices, or programs rather. So when we go to run a program, when we execute a program, so we double click on it or type in a command to run it, again, the shell is figuring out what we want to do, pass the instructions off to the operating system. The operating system has to go and find out where that executable lives right now. So, maybe it's off on disk someplace. It has to copy that collection of instructions, right? The executable is just this long sequence of instructions. It has to copy that into memory so that it can run it. And it has to figure out where the start point in that program is, where the first instruction is. So it loads that up, and then essentially it just repeats this cycle of grabbing the next instruction to run, figuring out what it is, and executing it. So when you hear discussion of the fetch, decode, execute cycle, it's just this repetitive cycle over and over and over again. Grab the next instruction, figure out what it is, do it. And again, this is going to happen millions of times a second on a typical processor. And more or less, this is the idea of your clock speed. Typically, the idea of the clock speed is how fast you can perform one of these fetch, decode, execute cycles. So if you've got a clock speed of however many billions, then it's running that many billions of these cycles, running that many instructions per second, more or less. Again, there's all sorts of gray areas and nuances to this, but that's the basic idea. So typically, we've got lots of programs running at once, right? There's all sorts of things running on your phone or on your laptop or whatever the device may be. There's a whole bunch of different things that are running simultaneously, or at least they appear to be running simultaneously. But if we've got, 50 different programs running, and we only actually have one processor or two processors or 8 processors or whatever it might be, clearly they can't all actually be running at once, right? Some of them must be frozen while one of them in particular has the processor, or one has each processor. So the idea is that the operating system goes and gives each program a short burst of activity on the processor. So it grabs program A that's pseudo running and gives it a fraction of a second on the processor. And then it pauses program A, stores its information away in memory someplace, and grabs program B and gives it a fraction of a second on the processor. And then pauses that one and grabs program C and gives it a fraction of a second. And if those are the only 3 running, then it goes back to A again and gives it a fraction of a second. So you've constantly got this process of running one of the programs for a tiny burst, just a handful of instructions, pausing it, giving the next one a turn. So you've got this kind of round robin cycle going on. Now, because there's millions of cycles per second, as far as the user is concerned, it looks like they're all running simultaneously, even though they're all actually, starting and stopping and starting and stopping over and over and over again. It's just happening too fast for us to pick up on the difference, for us to actually notice that these things are all kind of stuttering in their behavior. So the programs themselves, these executables, again, they're just thousands or millions of instructions, each instruction represented by some specific bit pattern, some specific pattern of zeros and ones. So way back in the early days, the way that things were programmed was by actually programming out this sequence of zeros and ones, ons and offs, switches. So the notion of going, okay, well, if I've got a program that's 1,000 instructions long, and every instruction is 8 bits or something like that, then I've got a sequence of 8,000 zeros and ones that I have to get right for the program to do what I want. So of course this was tedious and error prone, and so in around 1947, Kathleen Booth and von Neumann realized that, well, what we could do is instead of a human writing out these zeros and ones, what we'll do is give each pattern a nickname, add, move, whatever it might be, that's more intuitive for a human. So if 1101100 was add, then we'll just keep a list of what different names to associate with which different patterns. And so what we'll do is the human will edit a text file that's written in terms of adds and moves and whatnot, and then we'll have a program that will translate those, that will read the text file of adds and moves and translate them into the actual bit patterns that match them. So somebody first time around had to write that assembler, that program, the translator program, in zeros and ones, but once they've got that, then you can improve it around writing a new one using adds and moves and whatnot. And it's a lot less error prone, it's a lot more intuitive for the programmer to work with these names rather than with the patterns of zeros and ones. So huge improvement, development gets faster, gets easier, gets safer, gets more reliable. But you've still got a program consisting of thousands or millions of these little tiny instructions, these adds and moves that are all very fine grained. So the next idea was to say, well, why don't we make a language that's even more intuitive for humans. This idea of a higher level language where we introduce things like loops and if statements and whatnot that have a much clearer structure and are much more obvious for a human to understand. And so what we do, in this case it was Grace Hopper that came up with the idea, again, come up with a syntax for your high-level language, and in assembler, write a program that will translate that high-level code into assembly language where the assembler can, an assembler can then turn it into the bit patterns of zeros and ones. So this notion of a compiler was something to translate the high-level languages into something usable. So now the programmer can write in something that's much easier to work in. So first high-level language, first compiler, and of course you know now that there are thousands of languages and even more compilers out there that specialize in different kinds of application or for different platforms or for different devices. And again, things are much easier for us now. At the end of things, it's all still turned into these patterns of zeros and ones, but we've got programs, the compilers or the assemblers, that take the translation for us. So we write in a plain text file in a nice high-level language, and the compiler or assembler takes care of everything from there. Well, assuming everything actually works out okay. So yeah, most of our modern programming is done in a high-level language, C++, Java, whatever it might be. So the developer writes their code, runs it through a compiler to produce an executable, or to produce a ton of warnings and error messages indicating that they have to fix things. But eventually you go through the process of getting your code debugged, it compiles, and you can go off and run it. And then the one other thing that I wanted to mention was the idea of an interpreter, which is much like a compiler, except that instead of taking your program and translating the whole thing into an executable, it takes instructions one at a time. So you type in an instruction, it reads the instruction and executes that instruction immediately. Or if you have something like a script, it reads through the script one instruction at a time, right? It reads the instruction, the high-level instruction if you like, and executes it. Reads the instruction and executes it. So it's got a lot of the same work to do in terms of interpreting what you've written at a high level into something that can execute, but if you like, it's doing it in real time. It's doing it as you type things or as it reads the instructions, rather than doing all of the translation and then running the whole thing. So same basic ideas, and of course this is what's going on with something like Bash, right? We've got our Bash interpreter that's reading our Bash script or our Bash instructions and turning that into something that it can actually execute on the spot. All right, so that was kind of the background I wanted to go through just to make sure we're all on the same page when we start talking about details of compilers and automating compilation and whatnot. All right, we'll get there next.